So good afternoon, everyone. Today we are here for the lecture of product design engineering. We are taking a lecture previously. So we are going to continue the lecture which we have discontinued in the last session. So a little bit review we are going to take before starting a new point. So if you see in the previous lecture in detail, we have seen two products. So first product which is called as an incandescent bulb, and second product is an halogen bulb, isn't it? In detail, we have seen what are the different parameters which has to be considered while developing this kind of a product. This incandescent bulb and halogen lamp. Why I have taken this product? Because you are very much familiar with this kind of one product, and it is of household. This product is a household use, and you are seeing it frequently at your house and anywhere. So I have taken these two kind of product as an example so that you can understand very clearly, and it is related to some how with electronics also. So I have chosen this kind of a product. In the previous lectures as well as during the practicals, I have told you that you can consider any product as per your choice, but since you are having the background of an electronics and telecommunication ENTC branch, so choose such kind of a product which gives the which has the internal components of electronics, isn't it? So last time you had taken the example of a laptop, charger, again a pen drive, again CPU, isn't it? So many electronic products are there, and you have to open to see what are the different internal components of that product, and you have to study in detail. So in this lecture, we are going to continue from previous slides. So if you remember this halogen incandescent and halogen bulb we have seen. Okay, so this innovation map I have explained about the incandescent bulb. So what are the different materials it is used, what are the process to develop this incandescent bulb, technical differentiation, again a product technology, what are kind of product technology it is, and at last a customer value proposition, isn't it? So this kind of an now if you see this halogen lamp also we have explained. So what is the what is the difference between incandescent and halogen lamp? So that understanding is important, isn't it? So incandescent lamp you are familiar. As I said, 10 to 15 years back, we was having a some kind of a bulb which is made up of a glass coating, and internally it has a V shape of wire, and to connect to that wire, we are having a very thin tungsten filament is there, isn't it? A thin tungsten filament which has a very high melting point. So that bulb we call it as an incandescent bulb, isn't it? So recently it is not used because the evolution and innovation in that technology, this kind of bulb it is outdated, so it is not used. But you should know what was the initial technology we were using. So comparison of incandescent with the halogen lamp we have done. So halogen lamp where we can use, it is used in the street light, isn't it? Mostly the street light. And also we have seen what are the different properties of this halogen lamp so that it can sustain for a long life, and it can sustain the higher temperature, isn't it? So this also we have seen. Now moving to this new point, this LED. Actually, this is not a new. We are very much familiar with this LED light emitting diodes, isn't it? Light emitting diode is there. So my voice is audible to you. Can you hear me clearly?
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you. Okay. So what this LED light emitting diode? So this is you are learning the first year or the second year, isn't it? But if you see on the screen on the PPT, there are the different colors of the LED and different shapes of LEDs there, isn't it? So if you see for some LEDs, mostly all the LED is of two terminal, and one of the LED it is of three terminal, isn't it? And also if you see the shape of each and every LED, it is different, and color it is also different, isn't it? Now, if you see the LED, it is a light emitting diode. Mostly, if you see this light emitting diode, mostly it is used as a light indicator, isn't it? It is used as a light indicator in electronic devices. So not it is not only restricted to an as an indicator to an electronic devices. It is used in the car as an headlight. It is used in the vehicles, two-wheelers as an headlight. So because it consumes what is the property? Because it consumes a very low power and it uses much more light as compared to your regular, which was a yellow color bulb, isn't it? So instead of that, the LED it is much more popular. Now, if you see why this shape it is different, why the color of each and LED it is different, and the terminals it is 2 or 3. So if you see in detail, so if you see this slide, it shows the internal structure of an LED, isn't it? So if you see clearly, most of you have used the LED while doing the projects, isn't it? Your mini projects, as well as if you are a diploma student, you have done the projects in last year, where you mostly all of you have used the LED, isn't it? So, but if you see the internal structure of this LED, so if you see the encapsulation of this LED, it is mostly of an epoxy lens, isn't it? The casing which is done to protect the internal circuitry of this LED, it is epoxy lens. And internally, if you see, it is a wire wound part is there, and there is the connection between the wire wound and semiconductor die, isn't it? If you see the internal structure, the yellow part is there at the center. So that yellow part we call it as an reflective cavity. Is a reflective cavity, and this reflective cavity it is connected with the anode terminal of an LED with wire bond, isn't it? So there is a connection between the anode of LED with the reflective cavity by the means of an wire bond, isn't it? So why it is there? Why it is so? Why it is so? The reason is what? If you remember the working principle of an LED. In working principle of LED, two types of junction is there, isn't it? So p-type junction and n-type junction is there. So there is an interconnection between this p-type semiconductor and n-type semiconductor, isn't it? So if you see below the structure of this LED, again we have two terminals, anode part which is denoted by a positive and cathode part which is denoted by a negative sign, isn't it? So you are very much familiar. Now, if you see the internal construction or the principle, how does it work? So if you see the LED, it is a light emitting diode. If you see the function of this, it is same as an PN junction diode, isn't it? So if you see when you keep this LED at the room temperature without giving any external source or without giving any external supply, even then also it has a depletion layer, isn't it? So this depletion layer we can call it as a potential barrier. So this potential barrier, what it does? It doesn't allow the holes from the p-type to enter into an n-type, or the electrons which is there into an n-type junction, it will not flow into a p-type junction because of this barrier, isn't it? So that barrier we call it as a potential barrier. It it acts as a partition between the p-type and an n-type, isn't it? Now to make this LED or make this LED to work out. So what we have to do? We have to connect an external battery. We have to give an external source to this PN junction diode, or we can say it's the LED light emitting diode. So if you give a supply, that means properly if you connect the positive terminal of the battery to a p-type and negative terminal of the battery to an n-type, then what will happen? What will happen? By giving an external voltage of minimum 0.3 volt and 0.7 volt. This is the range, 0.3 volt for silicon and 0.7 volt for the germanium. Such kind of an external voltage, then what will happen? The electrons which is there in the n-type, as a majority carrier, it will try to cross the barrier. It will try to cross the barrier, the depletion layer, and some of the electron it will enter into a p-type, isn't it? And as well as the holes which are the majority carrier in the p-type, it will try to move into an n-type by crossing the barrier. So by doing this, by applying an external source, by applying the external voltage to this LED light emitting diode, what will happen? There will be a recombination of holes and electrons at the center, isn't it? There will be a recombination of holes and electrons at the region of that depletion layer, which we call it as a barrier. So because of this, what will happen? This recombination of holes and electrons at the partition of p-n type this recombination, it tries to emit the energy, isn't it? It tries to emit the energy in form of an light. So that is the working principle of your LED, isn't it? So LED, how does it produce the light? By giving an external supply to the diode, 0.3 volt or 0.7 volt. What will happen? The electrons, which are the majority carrier in the N type, it will try to cross the barrier, because external voltage, it reduces the depletion here. It reduces the barrier. So the electron can easily move to a P type, and some of the holes, which are the majority carrier, it will try to move or try to cross the N type, and it will enter into an N type. So at the center of this P type and N type, we form an recombination of electrons and holes, and this recombination of electrons and holes, it will lead to formation, or it gives the energy in form of a light, isn't it? So that light, it may be a green, it may be a yellow, it may be a red, it may be a white, anything, any color of the light, isn't it? Okay. Now, if you see below, there is an Fermi level graph is there, isn't it? Fermi level, you are also familiar with the Fermi level graph. So what is this graph? It shows when the electron, which is the majority carrier in the N type, when it enters into a P type, that means when it crosses the depletion layer. So what will happen? If you see below line, if you see the bottom line, so here there is a recombination of holes and electrons takes place, isn't it? If you see the orange color electrons and white color of holes, the recombination of electrons and holes takes place. So this recombination of holes and electrons, it leads to production of an energy, isn't it? And that energy is nothing but a light is thrown out from the cap, from the casing of an LED, isn't it? So remember this conduction band and valence band. So conduction band means what? The electrons which is there at the N type, and which is of the negative charge, and holes which is there as a majority carrier in the P type. There we call it as a valence band, isn't it? So the electrons, it moves from the conduction band to valence band when we apply an external voltage, isn't it? And after applying this external voltage, the some electrons, it crosses the barrier, and they enter into an valence band, and this movement of electrons from conduction band to valence band, it leads to production of light, isn't it? If you see the some zigzag curve is there of orange color, it shows the production of, or it gives the emerging of the light from the LED, isn't it? So this is an general LED of emitting diode, isn't it? Construction. Now, is there only one type of an LED is there? Isn't it? It is not. The answer is no. There is no only one type of an LED. There are the different types of LED based on the requirement, based on the customer requirement. The different LEDs, different specifications of LED is manufactured. But if you see the working principle, the working principle of each and every LED, it remains the same, isn't it? It doesn't change, isn't it? Now, if you see here, a different, if you see on the left side, a color are there, isn't it? So if you see at the top, the color, it is black, red, orange, yellow, green, blue, violet, purple, and this ultraviolet, isn't it? So these colors are there. So LED, it is available in this kind of an different colors, isn't it? And if you try to study the wavelength, what is the wavelength and what are the required voltage for that particular LED, it is listed in that column, isn't it? Now, if you choose a very top, very bottommost LED, is the ultraviolet, isn't it? Ultraviolet. If you look at the bottom, ultraviolet. So ultraviolet LED, it is what is the wavelength? The wavelength, it is less than 400, isn't it? The wavelength, it is. So why I'm telling you, because by looking at this chart, some comparative study will be there, isn't it? Some conclusion will be there, and that conclusion you have to remember it forever, isn't it? Why only one LED is not manufactured? It is not manufactured. Why only one? Because the reason is what? Only one LED, it will not serve the purpose of the customer, isn't it? The customer requirement, it is different, and based on that requirement of the customer, the shape, the design, and the specification of LED, it also goes on changing. Now, if you see the ultraviolet, in ultraviolet, if you see the wavelength, it is less than 400, and if you see the desired voltage, it is 3.12 4.4, isn't it? Their voltage is 3.1 to 4.4. So, and if you see the material which is used for manufacturing this kind of an ultraviolet, it is the diamond, boron nitrate, aluminum nitrate. So these are the aluminum, gallium, indium nitrate, isn't it? So these are the material which is used to manufacture this kind of an ultraviolet. Now, if you move up, isn't it? If you move up, so the purple color LED, again, it has the multiple types wavelength. It is not of a single wavelength, and voltage it ranges from 2.48 to 3.7. So 3.7 is the max voltage, 2.48 is the lowest voltage. And if you see the material which is used for manufacturing this kind of an LED, it's the blue red combination, blue with red phosphor and white with purple plastic, isn't it? So these are the combination of to manufacture this kind of an LED. So to manufacture one LED, one has to know what kind of material is required, isn't it? What kind of material is required to manufacture that kind of an LED. And if you see above purple, there is a violet. So wavelength it is 400 to 450. Voltage it is 2.76 to 4. Again, it is an indium gallium nitride is here. If you see for blue, it is 450 to 500 wavelength. Again, the voltage is 2.48 to 3.7. If you see from bottom to top, the wavelength is also goes on increasing. And for some LEDs, the voltage is also increasing, isn't it? Voltage is also increasing. So if you observe it carefully. So for blue, it is 400, 450 to 500, and for voltage, desired voltage is 2.48 to 3.7. And if you see the material, it is zinc selenide, indium gallium nitride, silicon carbide, and silicon as a substrate it is used. Now, same if you see or if you study this chart in the same way, you will observe that from bottom to top, that means from ultraviolet type of LED to infrared LED, what thing you observed in the wavelength, isn't it? So what thing you observed in the wavelength, can anyone answer? See the wavelength from ultraviolet to infrared, isn't it? From I move from the ultraviolet to purple, purple to violet, blue, green, yellow, orange, and red. So what thing you are observing in the wavelength? Whether the wavelength it is increasing or whether it is decreasing. Anyone can answer whether the wavelength it is increasing or decreasing?
Increasing.
Increasing.
Good. So a wavelength, if you see the wavelength, it is increasing. So remember, so for ultraviolet, the wavelength is very low, and if you see the red or the infrared, so wavelength it is high, isn't it? So red it has the wavelength it is high. Why? Can you tell me? Even if you see the red color of LED from far, if you see the red color of LED from a long distance, you can easily recognize that this is an red color LED, because the intensity or because the wavelength of this red color it is much high, isn't it? It is 610 to 760, isn't it? What is happening here? So, okay. So if you see here in this type of an LED, the wavelength it is increasing, isn't it? From ultraviolet to infrared, isn't it? So infrared it shows the higher wavelength, it is 760. And now if you see the voltage, so voltage it is from for ultraviolet it is 3.1 to 4.4. Again, where it is maximum, if you see the chart, for this type of LED, we need a higher voltage. If you see, we need a higher voltage. The higher voltage, if you see, it is required at the ultraviolet, isn't it? It requires at the ultraviolet. So it is 3.1 to 4.4, isn't it? If you compare ultraviolet voltage 3.1 to 4.4, it is the highest voltage which is required for ultraviolet, and wavelength it is lowest, isn't it? So wavelength it is lowest, isn't it? And if you see for the red color or the infrared, wavelength it is highest, that is 760 for infrared, and the required voltage it is near about 1.9. So what kind of conclusion we can make out from this chart? what kind of conclusion we can? Is there any relation between the wavelength and the required voltage? Any conclusion we can make out? So I can make a conclusion. That for ultraviolet, if you see, as you go on for ultraviolet having a very low wavelength, for a very low wavelength of the LED, the required voltage is much high. And for having a LED of high wavelength, that is of infrared, which is 760 nanometer. So this kind of wavelength, which has a very high wavelength, this kind of an infrared LED, it requires a very low voltage, isn't it? That kind of conclusion I can make out, isn't it? Yes or no? Yes or no?
Yes,
Isn't
sir.
it? So, yes, yes. So this thing you have to remember. So proper analysis, isn't it? Proper analysis of being as an engineer, you should remember in the mind that the LED which has a very high wavelength, just like an red or the infrared, it operates or it requires a very low voltage. It is 1.9, isn't it? It requires 1.9, and the LED which has a very low wavelength, they requires a much higher voltage as compared to infrared. So this kind of conclusion you have to make out. Okay. So this thing you have to remember. Again, if you move, to next slide. Just wait. Slide, it takes a time. To the next slide. Okay. Now, this is what regarding the white LED. So white LED, it is a mixture of three colors. So we are very much familiar. In the previous lecture, I told you that three colors are the primary colors, isn't it? Red, green, and blue, isn't it? So combination of these three colors. If you mix these three colors, you get a white color, isn't it? So this is the importance of the three color, isn't it? So by combination of any two color, you can make a secondary color, isn't it? If you mix red and green, it gives a different color. If you mix a blue and red, it gives a different color. If you mix green and blue, it gives a different color. Now, what thing you have to see here for this white LED? That means white LED means what? Which kind of white LED which used in the automobile, isn't it? At the headlight for your automobile car or two-wheeler, isn't it? So if you see this graph, isn't it, which is on the right side. So what this graph it shows that it shows, if you see on the x-axis there is a wavelength, isn't it? So the wavelength is varies from 300 to 350, 400, 450, 500, 550, 600, 650, 700, 750, 800, isn't it? That means from 300 to 800, it shows the wavelength on x-axis, and y-axis it shows the intensity, isn't it? So intensity from 0 to 500,000 and like that up to 4,000, isn't it? So this is the graph which tells the behavior of a white light. It tells the behavior of the white light along intensity versus wavelength, isn't it? Wavelength versus intensity. Now, if you see the graph, it is not a linear, isn't it? That means if you go on increasing the wavelength, the intensity increases. That is not the thing, isn't it? So if you see for different colors LED, it shows the different graph, isn't it? Now if you see the graph, it shows the peak, isn't it? Peak at 3,500, isn't it? It shows the peak. Now if you see, if we trace the peak below the y-axis, so what is the wavelength? The wavelength, it is near about 450, isn't it? So if you see the peak intensity, it is 3,500, and if you trace the 3,500 peak with the below x-axis, it shows on y-axis at 450, isn't it? 450. Now if you see the range, 450, 400 to 450, and from 450 to 500. So which kind of color it is? If you see which kind of color it is, from 400 to 450 and from 450 to 500, where you have a highest peak, that is highest intensity peak. So if you see the previous chart, from 400 to 500, which from 400 to 500, if you see which is the color, it shows 400 to 500. The color, if you see, it is a violet and which one? Violet and
Blue.
good. Violet and blue, isn't it? So violet and blue, these two LEDs, these are the two LEDs whose wavelength it ranges from 400 to 500, isn't it? Now come to that graph, isn't it? From 400 to 500, remember the color, it is violet and blue, isn't it? Now, if you see on the x-axis, we are having somewhat V is written and B is written, isn't it? So V stands for the violet and B stands for the blue, isn't it? That means for violet and blue color, remember for violet and blue color, whose wavelength is 400 to 500, whose wavelength is 400 to 500, for that color, for that only two color, which has the highest peak of 3,500 intensity, isn't it? Intensity, isn't it? So for these two colors only, your LED, it shows the highest intensity, and for other colors, that is for green, yellow, orange, red, it shows the less intensity as compared to violet and blue. So this thing we have to remember. Now, if you see on the top, it is written GaN, isn't it? It's the indium gallium nitride. So these are the manufacturing material which is used to manufacture this kind of an LED, isn't it? Now, if you see, again, if you move on the x-axis from 500 to 800, so again, if you see, it is not the peak, but somewhat it shows the rising, isn't it? Rising from 500 to from on x-axis 500 to 700. It shows what? From 500 to 700, it shows a moderate rise in intensity, isn't it? So what is that moderate range? From 0 to 1,500, isn't it? From 0 to 1,500. So these are the moderate range or moderate value of an intensity for other LEDs, which is green, yellow, orange, and red. For red, if you see, for red, which is of near about 700